Welcome everyone to our first small talk about big data for this semester. Today we have Dr. Daneshmandbi telling us about the implications for the Internet of Things as they relate to business intelligence and analytics. And I think you'll all enjoy today's presentation. So with that, Dr. Daneshmandbi.
Thank you, Chris. So I think the biggest challenge of big data is to give a small talk on big data. And in particular, small talk on the essentially three things you see here. The Internet of Things, big data, analytics. So I'm going to really talk about three things: the Internet of Things, big data, analytics, in a small talk. So keep in mind that when you are giving a presentation, when you want to interview somewhere, you want to have three things. First, tell them what you are going to tell them. Then tell them, and then tell them what you told them. Okay? So the first thing I want to tell, so I'm going to tell you these things: Internet of Things, big data, analytics. The Internet of Things is the first item. It is also called machine-to-machine, smart planet, connected world. Machine-to-machine, I think, was the initial name. I think came from computer scientists. Smart planet is the name I think IBM tossed as a smart planet. And connected world is what the, as far as I know, the telecom companies and the internet companies like that, connected world, because they were making money from connection and communications. So connected world, connected life. When we were going to propose a new journal called Internet of Things to the IEEE in 2010, we saw this picture at Economist 2010. And we liked it. Holy cow. In the world of IoT, even cows will be connected. And we attached this to the proposal we had for the IEEE for a new journal. And people liked it. I mean, all the editors, and you know, IEEE is a big organization, et cetera, et cetera. We could get the approval for the new journal, which is going to be started next year. And if there's a time, I show you the call for paper. So that's the diagram I want to share with you, the first one. And one thing that when it started, we all thought it started in 2008, 2009. But actually, on a recent paper, I understood that Kevin Ashton, on RFID Journal in 2009, he said, and this is true, that the Internet of Things started life as a title of a presentation Kevin gave to the Procter & Gamble in 1999. So in 1999, he really started the Internet of Things. It is not just a barcode, et cetera, et cetera. And the only one sentence here I want to repeat, because I want to come back to it. On that time, he said it has the potential to change the world. Potential to change the world, as did Internet. So I just want to draw your attention to this word, this sentence. I want to come back to it. But officially, the IoT was born on 2008, 2009. So what is it? Definition. It refers to, these are all important, uniquely addressable objects. Uniquely addressable, distinct objects, identifiable, et cetera, that are in an internet. It is an inherently cross-industry effort. I'll demonstrate why it's cross-industry effort and why we get involved. Because this seems to be a very engineering problem, yes. Well, yeah, but at the end of the day, you will see all these devices, what are they going to do? Generate data. and unless you intelligently manage, which he does, and analyze the data in a meaningful way, you cannot make intelligent decisions. So it is an inherently interdisciplinary effort. I'll tell you what are they. There are sensors, RFID tags, this is radio frequency identification tags, mobile phones, you just name it. Everything which is addressable, and I tell you what does addressable mean, and is connected to the network. Most of you know all of these things, but I repeat it anyway. Cisco says IoT is simply the point in time when more things or objects were connected to the internet than people. It is essentially devices, RFID tags, sensors, etc., plus networks, multidisciplinary, cross-interdisciplinary, plus services, plus data, plus analytics. Here is where we get involved, data and analytics. And in order to get involved on this part, like any other data-related problem, you want to know where the data comes from, what are the devices produce the data, you have to have some general understanding of it, okay? We do not design blood pressure measurement things, but we know what does blood pressure do, or that device do, generates a data. And if you use it for so many people, for so many times, so much data is generated from which you can make decisions. So therefore, to the extent that what does sensors things do, we talk a little bit in the course we are going to talk about and in this talk. So many definitions. I like this one this is a software company. IEEE has a definition. ETSI, this is the European communication, whatever. ITU is the world. They have all definitions. This one is good. Is a world where physical objects are seamlessly integrated into information networks and where the physical objects can become active participants in business process. Services are available to the internet, and therefore at the end it says intelligent decision comes from the data, and there is privacy issues. I'll mention that. Okay, so when it was really created, in 2008, between somewhere 2008 2009, the number of devices, number of things connected to the internet became equal to the number of human beings. In 2010, the numbers are 12.5, 6.8. 6.8 people in the world, 12.5 devices, billion. In 2015, it's going to be 25.7.2. In 2020, it's going to be 50 billion. 50 billion devices generating data all the time. All the time. And we do not have the luxury, which I'll come back to it, to have this data sitting somewhere, and we come back to it and analyze it and mine it. So it is a real-time issue of analyzing becomes so critical that it's going to call for a new generation of the algorithms, a new generation of database management systems, which in fact Stanford created something which is called data stream management. They call it DSBM. I'll touch on that. So where does it work? You remember I said potential to change the world? You just urban planning, smart cities, sustainable environment, healthcare, emergency response, waste management, intelligent shopping, a smart product, smart meters, smart homes, smart automobiles, smart agriculture, smart cows, smart grid, intelligent business decisions, marketing, inventory sales, etc. Smart cities, for example of a smart city, some of you, I think, I got you involved in the project which is happening on upstairs. It's the Hoboken Smart City, which they are collecting data about the city of Hoboken, from which you can so many things you can about the parking, about all these things, and they have data that those of you who want to do project, you should work with them. That's a smart city, and apparently we are a little bit ahead on that area. We, I mean, our school and the system school. Some examples: connected things like Apple's smart garment, tooth tattoo for the cows, which Princeton predicted that we can have a tattoo on the cow's tooth and we can predict if they are sick or not. Smart clock, which Google proposed. Smart metering, you can, okay, wind turbine, you just light, etc., etc. Okay, you can read all of this. I'm just giving you some idea that where the data is coming from, what's the scale of the data, and what is the characteristics of this data. Some of the people in this room knew about it on the middle of 1995, that the data will come on the streams. People, Dave Belanger, who was doing the telephone data, which was for the operations and all these kind of things. So the era is going to be like that, the streaming data. The smart transportation, the smart homes, the smart cities. See, weather sensors are all across the city, connected wearable health monitors, people are connecting it, surveillance cameras. I heard there are, I forgot, there are large number of them in London, that they are producing data all the time. Different data, streaming data, okay? Connected the smart, and all of this falls under the streaming data. IoT is one particular case of a streaming data. A smart world, okay? Air pollution, fire detection, forecast fire detection, this one you liked it. Wine quality enhancement. I just read these three so that I read this one. The rest you can read. And NSA gave a talk in Globecom, and I borrowed this slide from them. No, I meant NSF, National Science Foundation. Environment sensing. No, they don't give a slide. Environment sensing, unlimited applications, emergency response, smart healthcare, people-centric sensing, everything. So what are the technologies? I'm not going to read all of this. It is going to be sensors. The electrical engineers are working on the sensors, and people on the network are working on the networks and internet, because all these things have to be connected to each other. Software architectural, middleware, and somewhere, sensors data management. It is different from any other data management. Big data and data mining, again different. Distributed storage, data fusion, distributed sensing and control, resource management, and access control. This is the area of interest to us, okay? And the rest of the technology, the services and service implications of it, and then also social impacts of this IoT, which this part, privacy and security concerns, is part of our work, should be our concern, because we are data mining and we are extracting knowledge from the data. With that, so the system looks like that. Okay, none of us know about all of these things. At least I don't know. There is a thing domain, and a lot of research on that area, a lot of paper, etc., over the last 10 years. There is a device domain, like RFID tags, like wireless, like this, all of this, RFID tag. There is a network domain. How do you do all the protocols and routing and sending the data? And there is a core network here, and there is a service and applications. And at the end of the day, the raw data is generated. And therefore, human being is getting all this raw data and must make the intelligent decisions in every sense, in the business and operation, on health care, on everything. A lot of research has gone on these areas. These areas are pretty well good now. The thing which is really wide open to those of you who are in the area of you want to do your PhD thesis or whatever is the data streams management and data streams analytics. A lot of open problems, a lot of research problems. I'll mention it as we go forward. This is another case in which I like that one because if the weather is bad, the sensors will communicate your clock at your bed, and the clock would turn on the coffee maker a little bit sooner, and also would communicate with the taxi to come 1 hour sooner. Things like that, okay? So this is going to be, but all of these are going to be big data analytics and big data as a service. And one more last slide on the Internet of Things. Sensors, stream analytics, real-time analytics, mathematical statistical analytics, machine learning, big data analytics, okay? I'm done with the 1/3 of the talk. I'm going to talk 2 slides about big data. So Internet of Things, I hope I communicated, of course, the professors here know, most of the students know, but I just wanted to say, look, a lot of data is going to be generated by these devices. And I tell you the scale later. Big data. In fact, the term was first introduced by Roger Magoulas in 2005. This is ASA latest article, says the term of big data was introduced in 2005. We all know about McKinsey Big Data, which came 2011. We all got excited. White House allocated a lot of money to do research. New oil. Somebody said it's new oil. I don't know. I forgot. Okay. Cliff Humphrey said this is the new oil. I'm talking about big data now. And Electrical Engineering Times said the emergence of IoT has created such a flood of data that only a state-of-the-art IT can gather, filter, and so forth. So this is the IBM, I'm sorry. The IBM, VP of Research at IBM wrote an article in 2012 on Electrical Engineering Times said that. And New York Times said there is no area, talked about big data in 2012, there is no area that is going to be untouched. You can see it. And this year, McKinsey's article or research which says identifies 5 big opportunities for US growth. Big data is one of them. How big is it? Big data is big, but let's focus on the only IoT data. Somebody who is sitting here, Dami, brought to my attention that on 1833, there were only 2 nodes and 1 link. That when that started, something, when telegraph or electrical telegraph started. Okay, now, you remember I said identifiable, addressable devices. How many we can do? 2 to the power 128, because this is IPv6. IPv6 enables you to have 2 to the power 128 devices, addressable, distinct, identifiable, connected to the network, or connect as a subset or whatever. And that 2 to the power 128 is this number, 340 with all these zeros. How many are they? What is this called? This number is called what? Say it again. Undecillion. Okay, I can't say that, but undecillion. So there are so many nodes, 2 to 128 nodes. And in practice, how many links could be there? 2 to the power 128 to the power 2. To be very specific, 2 to the 128 times 2 to the 128 minus 1, because you are not counting the one which, okay? So there are so many nodes. Imagine a world in which there are so many nodes, all of them generating data, and there are so many links. Oh, okay. And then McKinsey says in 2012, there were 2,836 exabytes of data. And here I say, what does 1 exabyte mean? Equal to 2.5 times large as US library. I mean, they say, I don't say it. And they say in 2012, the highest number is investment services, banking, manufacturing, communications. Communications was number 1 until 5, 6, 7, 10 years ago. Now, apparently, I don't know how much this data is valid. And 32% in the US, 19% Western Europe, 13% China, 4% India, 32% the rest of the world. This is McKinsey's chart. And here is what does these things mean, okay? YB is 2 to the power 80. It's nothing compared to 2 to the power 128. Now we're going to talk about analytics. So Internet of Things, generates data, big data, and now a little bit about analytics. This is the major challenge in the two senses. One is data management, and one is data mining or data analytics. And of course, the third one is visualization, okay? I do not know about visualization. I do not know about database management systems. I know a little bit about analytics. I'm going to talk a little bit about analytics to put things in perspective, that where are we and where are we going and where are the open problems. Most of you know, I always showed you that chart, which is not my chart, came from KDD process, data mining process, is that there is a database sitting somewhere, a big database sitting somewhere, and then you come up with a profound question. You go to this database, select some items of the data, clean it, put it on data warehouse, select the task-relevant data, mine it, extract knowledge. I repeat this. You can come back to it as many times as you want to for either fine-tuning your last algorithm or coming back for different kind of profound question which gets asked. The bottom line is that this is sitting here, okay? But that seems to be a little bit old as we go forward. It's going to be, this thing is going to be changing all the time. I mean, there is no such a thing anymore. Data comes, and now there are some ways of putting on databases, but a lot of effort. So data arrive in streams, streaming data. I'm trying to define a streaming data. Data arrives in the streams. And Dave called it data in flight a long time ago. So with this, and this is a sentence from you again, Dave, the nature of analytics has changed. So data arrives in the streams continuously and so rapidly that it is not feasible or useful. Not useful. Because I want to know something on the real time. I want to know if the blood pressure of somebody is going beyond the level now. I want to know whether or not there is an attack to the network now, at this moment. We want to know if there is a fraud somewhere right now. Because, so it is not useful to put it in a database anymore. So it's feasible or useful to store it, and it is not feasible, of course, with so many data, in a conventional database. Conventional database. They are creating new type of databases, which I just know about it, but I don't know very much about the detail of it, and then analyze it at the time of our choosing. That's not anymore possible. Cannot put it here and come back whenever we have time to analyze it. It is, if it is not processed immediately, and by process mean managed, analyzed, then it is lost forever. And that's why the nature of the analytics has changed. Okay. Now that really puts a little bit on the static data. They call it static data. On the static data, the computer scientists came up with some names which are different from statistical mathematicians. But anyway, on the static data, there are multiple passes. You can come to that. Multiple passes means you can come back here multiple times. Adjust your artificial neural network, your parameters, your coefficient, until you are in good shape. In this world, there is only one pass, single pass. Data comes, you must use it and analyze it, otherwise you lose it. The persistent, relatively stable data on the static data, relatively stable, you don't update it all the time. Inherently temporal, continuously evolving. Offline analytics, online as well as offline. Analytics based on all the data. Analytics based on the subset of the data. Subset of the data. So the sampling and the inference and everything which was developed by mathematicians comes to picture again. Okay, I'll come back to that. So, okay, only the current state is relevant. Consideration of the order of the input is important. The order becomes important on the streaming world. Relatively low update, potentially extremely high update, little or no time requirements, real-time requirements. Assume exact data, assumes outdated, inaccurate data. Why? Of course, this is not perfect either. There's a data quality issue. But there's more data quality issue here because these sensors and RFID chips are sitting in the middle of ocean, and they are working on I know a little bit about it, on batteries, and battery may go down, and data may be bad, and so the cleaning the data becomes fundamentally very important, and on the real time must be done. Assumes exact data, assumes outdated, inaccurate data, planning query processing. Now, in this you can plan query processing. Here is variable data arrival and data characterization. Similar comparison, this is as far as analytics is concerned. Similar comparison about database management. This is database management system for static data. This is data stream management system. That's where a lot of work is being done at Stanford and some work in MIT to how to do data stream management system. Okay, because this is really a new environment. I'm not going to talk about that much, but I'm going to go back to the analytics. Okay, now here is good old again chart we used many times. Big data challenges and data life cycle on the stream world. There's a raw data, there's a collection, there's a cleaning, transformation, management, mining, interpretation, output. Okay, this has totally changed the nature of this arrival. And therefore, all of these things are being modified and or being changed. Okay, and I can spend a lot of time about collection and data quality. I may do some on my course, cleaning, a little bit on transformation, because now the good old statistics becomes to the picture. You can do the sufficient statistics. I'll define sufficient statistics rather than and let the data go. And take the sufficient statistics, let the data go. Sufficient statistics would help you to do the analysis. So I'll spend a little bit time on mining and analytics here. Okay, so here is the kind of scenario in a very naive sense. We have only M sensors or things. And these are some definitions. And each sensor generates a vector of variables at each time. And these are real numbers. And these are random variables. And here we define what does the data stream mean, the time and the value. The time is a single variable, but the value is a vector variable for each sensor. So if there are only 4 sensors in the world, at 9 a.m., sensor number 1, which is located at these coordinate points, generated 2.3. Sensor at the same time, sensor number 2 generated, which is located here, generated 1.1. At the same time, sensor number 3, sensor number 4, you see? And then at time 2, which is 15 minutes later, which is not again realistic, it's going to be every second. Every second. There's a work going on that there is a router, let's say, a very simplified sense, there's a router which handles 40 gigabits of data per second. And each packet, you can look at each packet which goes through this router. Either this packet is going to the Stevens domain or not a Stevens domain, okay? And it is very important to know that is the pattern of the packets going to the Stevens domain has changed. If it has changed, it has a lot of implication, security implications, okay? And therefore, at every second, you want to know of the 10 to the power 10 packets, past packets, how many of them are going to a Stevens or coming from a Stevens. Now look at this is a Bernoulli model, Bernoulli trial, 10 to the power 10 trials, 0, 1. And you want to estimate how many ones, suppose you call it 1, and you want to change the detection, detect the change, whether or not it's going up, going down. So you see all the problems. The problem is changing. All the problems of sampling, problem of windowing, time windows, all of these things become the picture of the analytics. Why I said that? Anyway, so this is the data. Okay, now a little bit about algorithms. Many existing data mining methods cannot be applied directly to the data streams. I hope this is obvious, because when I do artificial neural network here, okay, I designed a neural architect of the neural network. I come back and go through the back propagation or whatever and calculate the coefficient or weights, and then I test it against the data it never saw, and then I calculate error, and I come back and adjust the weight, and I go through that many, many, many times. This is not possible anymore. So many existing data mining methods cannot be applied directly to data streams. Still, there are some good things, but you have to modify it. You have to do some changes. Okay, so there are two things are emerging, two areas. That's where I really want to draw the attention of students and PhD students. Two areas are emerging. One is popular existing algorithms, like the ones we teach you, like C4.5, classification, clustering, artificial neural network. These popular existing algorithms, which they showed, which were designed and tested with the conventional statistic data, have to be adapted, modified for streaming data analytics. A lot of research and work is going on that area. Everybody is taking, how can I modify C4.5 for the streaming data? How can I modify classification and regression tree for the streaming data? So a lot of work is going on that area, adaptation of. And then, not only that, a lot of new emerging techniques. New in what sense? Not the mathematics of it is new, as I will explain, but applying it to the data streams is new. So I'll go over both cases. A lot of new emerging techniques are being innovated for management and mining of streaming data. On the popular algorithms, for instance, on the unsupervised world, clustering is a very important algorithm. We use a lot. It answers a lot of questions, used for initial decision, what do I want to do next? But of course, you cannot apply it to the streaming data. Remember, in the clustering, you have all the data sitting here somewhere, and you find the centroid and find the distance and calculate the centroid, and okay? You play with it until you find good clusters. Here, there is no such a thing. Data is coming in streams. So a number of guys from, researchers from IBM and I think Rutgers and the places I know, and the person in Portugal, several people did a lot of good work on modification of the existing techniques. They created what's called, for the clustering algorithm, they created what's called online microclusters. They do it in 2 steps. They create online microclusters. As the data arrives, they calculate certain sufficient statistics. By the way, sufficient statistics is a function of the data which mathematically has certain characteristics which you can conclude that the most of the knowledge and most of the knowledge is on that function. Example, an example would be, a naive example would be the mean. Mean is a sufficient statistics for estimating, sample mean is a sufficient statistic for estimating the mean. So if you really preserve the mean, you have 100 numbers are coming to you, you can't manage it. If you somehow can calculate the sufficient statistics, which is sufficient, let's say mean, and you keep that one, then maybe you can manage it, maybe you can come back to it and analyze it later. So they said something online macro, which is essentially the thing I said. They create clusters online, and they use cluster feature. Cluster feature, again, is some summation, mathematically speaking, summation of the numbers as arrived to you, but not simple summations. One of them is simple summations or other kind of summations. And step 2, now you can do offline, which is called macro clusters. This is very efficient, enable tracking cluster evolution, because as the data comes, you want to cluster it, you want to find cluster evolution. For the supervised classifications or decision trees, all these names, 2 famous one are C4.5 by Quinlan, CORT by Bryman, etc., which we teach in our course. They created what is called very fast decision tree algorithm. And very fast decision algorithm really uses good old Hoefting. You guys know Chebyshev inequality and Chernoff and etc. Hoefting also had a formula a long time ago that what is the probability of a given number exceeds certain level. So therefore they use this, and rather than waiting, what do we do in the classification? We look at all the data and then we create nodes, decision nodes, and separate them. Rather than waiting for overall statistical evidence in favor of a split, wait for the overall statistical evidence in favor of a split, not wait for all the data. Okay, we don't have all the data. So we have to do it for, when we see some statistical evidence of the differences, we do our clustering, but we are doing this dynamically. And the other one is, they call it online info fuzzy network. IFN algorithm applied to the sliding window. In this case, they use a sliding window. And now the question is that, what should be the size of a sliding window? Optimal size depends on the sufficient statistics. What should be the size of a sliding window? And then, by the way, these new techniques, just like in the good old day, the computer scientists called it exact answer. Okay? Now they call it approximation. It's not approximation, it's estimation. But this approximate estimation comes with a confidence level, saying, you tell me what's the level of error you want, we can tell you what should be the size of the window, what should be the sample size, so we can calculate things and analyze things by giving some well-defined error margins. So, so these are the modification of the popular existing. A lot of papers on that area. And emerging techniques. Sampling. You know that, I don't know, in the middle of last century, a number of people devised this sampling theory or sampling techniques because they could not see and observe everything. They took a sample. And then came a lot of different ways. How do you sample? What's the optimal sample? What's the optimal size? What are the different sample designs, etc., etc. Okay? And then they use probability theory to estimate things. Now, when the computing became very strong, computer scientists said, no, there's no need for sampling. I can look at all the data. Now, back again to the good old days, sampling. So these are new emerging filtering, wavelets, because see, the data, as I said, these are signals. And the signals you cannot do maybe sufficient statistics, but in some sense you can approximate the signals by sum of a number of well-behaved nice curves. Synapses and histogram. Synapses is the term computer scientists use for sampling. Entropy of a stream computation. This is becoming very important in the field of cybersecurity, because the entropy is a measure of how things are random or behave normal with respect to their past. So if you calculate quickly the entropy, and there's a change on entropy, you can say, oh, there is some change. A sliding window, I talked about it. You really want change detection, anomaly detection. This is kind of good old outliers. You remember when we used outliers to find the data point that is different from the rest and do not bring it the usual calculations? Now in this field, outlier becomes very important. Outlier is the one we are looking for. Something happened. This person's blood pressure, I always say blood pressure because I have blood pressure problem. This person's blood pressure is outside the normal. So therefore, we are looking for the outlier. We are not looking for normal, whatever that number is. Moment estimation, moment generating functions, bounds and confidence intervals, all those Chebyshev and all these things become important again here, not straightforward to apply it onto the streaming data. These emerging things, theoretically, mathematically, from a statistician, from probability people, from probability point of view, electrical engineer, mathematician, a statistician, these techniques are not new. But adapting and using these techniques to the streaming data and at this scale are really new directions. And here is some example of, again, he gave me that example, Kalman filter for finding anomaly. And this is another example of packets are coming and you want to do window. And then this is packet the sliding. And this is what I wanted to spend a few moments on it. Summary and conclusion, research opportunities. The stream data analytics domain is wide open, it's really open. I read the last item for you first. I have been spending a lot of time on that. There is no textbook, okay? There is no textbook. There are books came into this year and last year, but not textbook. They are not organized. It's mostly edited books and everybody wrote a paper. There is no even a textbook on it. So it is really wide open area. What are the things? Sampling tech designs. Okay, think sampling designs are so many sampling designs. Simple random sampling, probability sampling, cluster sampling, multi-stage sampling, stratified sampling, all of these can be applied to the streaming data. Because, for instance, a stratification, you want to stratify certain things which are in certain areas, which they look like each other, and take a sample from that strata, take a sample from other strata, okay, if you can do that. So all of these things are really open to the research. Sampling for time series. This is the time series. Okay, in that area, a couple of papers are published because when you talk about sampling, the fundamental theory of sampling is that I have n things, capital N things. I want to select small n things of the capital N things, and I want to select it in a fair, unbiased way, meaning equal probability of selection to all these elements. But when it's come to streaming, you don't have n. You don't have number of data points. How do you do sampling when you do not have n? Okay? So therefore, this becomes, and people came up with certain techniques which they do it. It's wide open. There are two algorithms I read. They are not fantastic, but they are okay. Okay, so sampling times, statistical inference and estimations. You remember computer scientists were looking for exact numbers? No exact numbers. Now we can do statistical inference and estimations with certain confidence. Sufficient statistics, I described it. What are the functions of this data? This is well-established theory in the field of statistics. Sufficient statistics is defined as functions of the sample which have most of the data. In fact, electrical engineers also have such a thing, okay? I think called information theory, or I forgot, I don't know, I'm not sure. So the theory of sufficient statistics can be used here. Outliers theory, there were a lot of theory on outliers for change and anomaly detection. And the last open problem is the first textbook on stream data analytics. So anyway, a lot of opportunities for those of you who are interested in that area. Questions? Suggestions? Comments?
We're going to change our, we're going to introduce a big data course in the program. How much else will we need to change in order to provide the necessary prerequisites for a big data course?
I think data stream management systems becomes important. And I think visualization. And of course, privacy. Because at the end of the day, I think our students, when they are sitting in Merck, they should, and they want to get the data, whatever, or with healthcare industry, whatever, they should be aware and know that, look, we need to anonymize this data. So that, as we do it, as Dave told us to do it many years ago, because when with the telephone call, we didn't know it's yours. Data was anonymized. You were a node in some space connecting to that node, and that was useful for network operations. That or a lot of nodes going to that location or not, or that was necessary. So the data was anonymized. So anonymization, our students should know, especially in that environment, saying, okay, there should be, we cannot, I don't think we can train people who can do anonymization. It's a hard task, but they should be aware of it so that they can bring it up.
Okay, there's one other thing that I think when you talked about the areas that we can do research in, I think there's an area of innovation and invention applied to mobile devices, but you didn't mention that. It could be something that a business analytics program could be involved in, because we don't know what the future is going to be. It's going to evolve into something wild and wonderful. And I think there's an area for us to think about what those applications could be, and develop them, invent them, test them.
I think we can, what I'm aware of, I think we can team up with these people who are putting sensors in Hoboken and generating data. We have access to this data. I used it for my students last year. I'm inviting him to give a talk on my class again, and the team of people are going to go and have access to that data. They need analytics. They love our students to do analytics for them. They raise the question, they give the data. And our students can analyze that data, and then this way, as Dave always says, if you don't have data, no matter what algorithm or whatever you invent, if you have to test it against the data. So I think in our case, the simple answer maybe is to having access to that smart city data and and use it. And the other thing would be stock market data, which we have. But I don't know. I don't think we have access to mobility data or something. We have to start with what we have. I don't know if I answered your question. Okay, I want to show just one. Give me one more moment. So there is a new journal for some of you approached me. So this is the Internet of Things journal. I already have somebody who is submitting paper from Stevens. So please submit journal. And that could be, or there are parts to it, which is the service applications, could be the data-related stuff, okay? So this journal can start with designing a new sensor or designing a new algorithm which can analyze that sensor data. And that's IoT IEEE org journal, and it's going to, 31 October is the due date for submission of paper. Now I am done. Thank you again.